So then we need to have two for loops to search these ranges. So this is my first for loop with the loop variable I that starts from 1 to the length of L range. Okay, and the second variable which runs with J, and that runs from 1 to the length of K range. Okay, so for each I and J values we have an example L value that is the ith element of L range, and the other one K is the jth element of the K range. Then we can generate our prediction about the variable y. So y is equal to L over, in parentheses, 1 plus exponential minus k times x. So x is a vector, so I'm going to use always a dot multiplication and also a dot division. So this y shouldn't be confused with the original one, so I call this y cap. Okay, so that means here we should have a cap that is usually used for predicted values. Okay, so this is y cap. So now I'm going to compute the error between y cap and the given y. Okay, so we can use the y cap value, or we can also call it y model. Okay, so this is the modeled values for y which obey a logistic function. So what is the error? Error is the difference of the model to the actually given y value, but in absolute values, because we don't want negative and positive errors to cancel out each other since we sum all the errors. Okay, if we are talking about an average error, we should divide it by the length of y. Okay, so this is average error. So here we get a number. So then we have to close the for loops. So what happens next? We calculate the error. So if this error is minimum, then that means these L and K values are the ones that we are looking for. How do we check this? We use the if block. We start an if and close it, and the thing is, what is going to be the close of the if? So if average error is smaller than our main error, okay, then we store these values. Then we say L main, okay, this is the L values we are looking for is equal to L, and similarly K main is the value K for our function is the value K, and similarly main error will be reset to average error. So this is what we are doing when we find a good combination for L and K that is smaller than our main error. So first we have to initialize this main error outside of the loops with a very big number. So main error is equal to 10 to the power 10. Okay, that is a very big number. So every time we find something smaller than this, we store it. But in practice, the first element will be automatically smaller than this main error. So in our search, first we reset our L and K main values to the first element, then we continue our search. Sometimes we get smaller values, which means better L and K parameters. Sometimes we don't, but the thing is, at the end we search for all possible values in our range and basically keep the one which gives us the minimum error. Okay, so let's run this part of the code and we get some values. For K main we get 2.7, for L main we get 5.1. So these are the best parameters in our range, and our range is sliced with the step width of 0.1. And let's see if this is a good fit. So first we need to define a best model. Okay, that is basically equal to this very same equation, but we have to use the main parameters that we have found. Okay, so this line will give us the best model. Okay, the best model is there. The y, given y is here, we already plotted, and now we are going to plot the best model on top of that. Okay, I'm going to hold on to keep the previous figure. Then I'm going to plot x versus y best model. Okay, the figure is there. And I'm going to plot this with a red trace. Okay. Okay, so this is our logistic function now. Qualitatively, we can see that it is a quite nice fit. So let's report the error on the screen. So what is the error for this best model? That is y best minus y in absolute values. So we sum it up, we take the absolute value and we divide it by the length of y. So this is the best error. Okay, let's run this. Okay, there is an imbalance in the parentheses. I just had an extra parenthesis which we didn't want. So the best error is, I can see from the workspace, it is just 0.5. So let's report this. Curve fitting on the command window, we use fprintf. And inside the report we say the best logistic function has these parameters. Okay, has these parameters. Colon L is 2.2f and k is the other number that we are going to report with an average error of this. Okay, I'm going to show you the full line. So here I promise to report 3 numbers. So I should give these 3 numbers. First number is L main, the second one is K main, and the third one is best error. And I'm going to finish my report sentence with a new line. So let's run this line, and it gives me the report about the curve fitting. Okay, let's save this. Okay, so I can run this very same line. So let's change the step size. We should get it not like a crude image, but let's have a finer range. Okay, it will take more time, but the logistic function could be a bit better. So now The average error is like 0.57. Let's see if this improves with the new L range. Okay, I'm going to run it. Now I'm waiting. Okay. Actually, the parameters that we found was not so different from the initial ones, and the error only improved in a small margin, and we actually couldn't see the difference. How can we see more significant figures? We can just change this value after the dot. Let's change it to something long, to 6 for example. When I run it, you see the actual average error is this, and with the previous version, when the range was sliced with 0.1 step sizes, it was, as you see, very close, but if you compare these two numbers, it was slightly worse. So here we can see that increasing the step size doesn't help us a lot, so it is better to keep this crude range so that we get a faster result, and we can graphically see the difference. With the step size 0.1 and with the step size 0.01, we don't get much qualitative difference to explain our data with a logistic function. So now what you can do as an additional exercise, you can use the same data set but with a linear function. Okay, instead of a logistic function, you can test a linear function, and then you can compare whether a linear function will give you a smaller or larger average error. If you get a smaller average error with a linear function, that is the better option as a fit to our data.